like the way I explain things? Are you tired of training yourself like a monkey to repeat steps on a test without understanding anything? Well, then you're in luck. Just go to inductica.org/contact and you can book a coaching session with yours truly. I cover all levels of math and physics, including very difficult subjects such as quantum mechanics. All right, back to the video. Awesome. Well, let's get right into it. So let's listen to a first clip of Feynman, and we'll be giving our reactions.
This shows, again, that mathematics is a deep way of expressing nature, and attempts to express nature in philosophical principles or in seat-of-the-pants mechanical feelings is not an efficient way. I must say that there is possible, and I've often made the hypothesis, that physics ultimately will not require a mathematical statement, that the machinery ultimately will be revealed, just a prejudice like one of these other prejudices. It always bothers me that in spite of all this local business, what goes on in a tiny, no matter how tiny a region of space, no matter how tiny a region of time, according to the laws as we understand them today, takes a computing machine an infinite number of logical operations to figure out. Now, how can all that be going on in that tiny space? Why should it take an infinite amount of logic to figure out what one stinky tiny bit of space-time is going to do? And so I made a hypothesis often that the laws are going to turn out to be, in the end, simple like the checkerboard, and that all the complexity is from size. But that is of the same nature as the other speculations that other people make. It says, I like it, you don't like it. It's not good to be too prejudiced about this thing.
All right, it's not good to be prejudiced about the idea that any one part of space or any one part of the ether has some kind of finite nature and some finite number of things are going on in that location. That's just a prejudice. So some background for anyone who's a little confused by this. He's referring to quantum field theory, which effectively gives an estimation procedure for the state of a quantum field at any one location, and that estimation procedure is an infinite series, which of course can't actually be finished, but you can approximate it by finishing part of that infinite series of terms. You can approximate what is happening quantumly at that location, and Feynman is saying, well, I'm biased, maybe. I don't think there's actually an infinite number of things going on at each location, but that's just a bias. Maybe really at the end of the day, all there is mathematics. So I picked this first because this really shows right off the bat that Feynman represents one of the things that's wrong with modern physics is that it's unphysical. And that might sound a little bit crazy to say, like I'm being over dramatic, but this is truly unphysical thinking. The idea that there might be an infinite number of things, a truly infinite number of things happening at every location, you are simply not using basic physical reasoning in order to understand what it is you're dealing with, in favor of simply accepting some mathematical framework and saying, oh, well, math seems to work at getting correct predictions, so maybe that's all there is. This is equivalent to Feynman telling Copernicus, like, oh, well, I understand that you have this simpler theory, and it might be right, and I certainly like it more. I like your simple theory where that it accounts for, retrograde motion with the planets going around the sun instead of around the Earth. But maybe epicycles are true, and maybe there's an actual infinite number of epicycles. Maybe the planets follow an infinite number of circles upon circles upon circles as they spiral around the Earth. For all we know, that's what's actually going on. Comments on this, Aviram?
Yes, I have a slightly different interpretation of what's going on here. I think that Feynman is trying to think about continuous things, like continuous processes and continuous fields, and he thinks of it like Zeno. He thinks of it like you have a continuum. It is composed of incountably, infinitely many points, And as a consequence, he arrives at the conclusion that if you assume fields, then you have infinitely many locations of activity, an infinite amount of activity going on in all of these points. But I think that one way of solving this is by actually getting to what is originally a point by Aristotle. When you decompose a continuum, you can only truly decompose it into smaller continua and the boundaries between them. So if you have a portion of the universe where there's field activity, you can subdivide it into smaller portions, but those portions are going to be of finite numbers. So in a sense, you will only be analyzing the field with finite parts of the region where these activities are happening. So you are never really dealing with infinitely many points undergoing infinitely many processes. And Feynman doesn't really hint at this solution, so he's trying to...
Yeah, but Feynman's, he's unaware of all of that. Yeah, sorry.
So he's trying to solve the problem by physical means. Instead of conceptually analyzing the problematic idea there, he says, well, I can avoid this paradox of infinite points with infinite activity by saying, no, there are no true continua. Everything is discrete, and the number of vertices in this discrete lattice or in this discrete distribution of points is finite, and so I have no problem with infinite processes. And this reveals something about his kind of Zenonist or atomist way of thinking. And I don't know if you notice that, but when he speaks about Maxwell's laws and the law of universal gravitation, he seems to be saying that there is some way in which these laws are unsatisfying. So the law of gravity, Newton's inverse square law, tells you what the force is, but it doesn't really tell you what's exerting it, how it is being exerted. And Maxwell's equations also, he thinks of them as, in a sense, you don't really know what's going on there. You're not.
Yeah.
You don't really get any insight.
And he's right about that. He's right. This is his better half. This is his, Feynman's spirit is better than his philosophy. Like, he wants to know what's physically going on. Like, the part of him that played with radios as a kid wants to know what's actually going on. But the part of him that was educated by Karl Popper knows that that's just a bias.
Yeah. It's not entirely satisfying.
Yeah.
Just saying it's a field and something is waving. And I think this is the subtext of what he's trying to say in these lectures.
Yeah, it's definitely a theme that we're going to keep coming up to. Now, what's the importance of this? I wanted to illustrate this for the audience. What's the positive case that Inductica would make for this? Is that we need to think in terms of entities and their relationships and actions with respect to one another. It doesn't mean we don't have to, but that's the goal. It's fine to have a theory that identifies general trends and then makes general statements about what will happen. That's fine, but we have to understand that whenever we have a theory like that, there is all of those general trends are the result of entities acting and relating with one another. So let me give an example. So let's take the theory of relativity. I was having a discussion with an objectivist physicist once, and I told him, well, special relativity is obviously, causally lacking. It doesn't have a causal structure. And he looked at me, he's like, well, what are you talking about? Of course it has a causal structure. And this was strange to me because another objectivist, someone who believed in Ayn Rand's philosophy as I do, they thought it was a causal, like it was actually causal, and I found that interesting. He said, well, how is it that it's causal? And over the course of some discussion, here's basically what his argument amounted to. It was Einstein identified, or I should say re-derived the laws of special relativity from Maxwell's equations. He showed that in order for Maxwell's equations to be true, space and time had to, I'm putting this in quotes because I think that's a wrong way of even thinking about it, but this is the way he thought about it. If Maxwell's equations are true, then space and time have to function in this particular way, including light being measured as the same speed in all reference frames. So so I said, okay, I see. You're saying that Maxwell's equations, in a sense, cause these special relativistic effects. And he said, yes. I said, okay, fine. We can see that Maxwell's equations require these other things to be true. But that's not a cause and effect relationship. A cause and effect relationship is when an entity acts on another entity. It's an understanding of the nature of one entity and how its relationship or action with respect to another entity involves some kind of other bit of identity or some change in identity. We want to understand these things in terms of entity because reality comes down to entities. If we understand the entities and what we're doing, that's what gives us real power to manipulate this stuff. But instead, we have this general trend of fields and this funny aspect of how they work and that they're, Lorentz invariant, and then that leads to a bunch of other effects. But it's not clear what the actual cause and effect relationship is. Now, this wasn't on the docket, but this is related to the way Feynman thinks about mathematics. There's another section, we're not going to be able to look at the part, but Feynman essentially says, he says, I like the Babylonian approach to mathematics, where there's no necessary hierarchy. You just take some of the ideas and you deduce the rest of the mathematical framework from that small set of ideas. You don't think of some things as being more important than others. So, like in the case of special relativity, what's the cause, what's the effect? We have no idea. You can derive the special character of Maxwell's equations from certain assumptions about symmetries, and you can derive something. I may not be saying that quite right, but it's something like that. And you can derive the aspects of special relativity from Maxwell's equations. So you could go either way. There's just some facts that necessitate other facts. But you can't go any direction you want when you're thinking about entities acting, because a certain entity with a certain nature requires something else to happen. You can't reverse that process once you actually understand the entities, because at the end of the day, one thing affects another thing. All right, comments, Aviram?
Yes, I agree with that. I don't think that Feynman belongs in the camp of the math worshippers, where they simply think of physics as a formalism that can't be really interpreted. But he is also not insistent on causal reasoning. He's I think, more of a pragmatist about these matters. So
yeah, it's whatever works. See? Yeah. Really quick for our audience, what we mean by pragmatist is specifically we don't mean that in a positive way. Now, in a broad general way, making practical application your primary standard, that's good. We're not against that. At the end of the day, you need to be successful. And if you aren't successful, it means you're doing something wrong. It means, because at the end of the day, this whole process, the only reason is to get results. So we're not against being practical, but we're against pragmatism, which is a philosophy which says that there are no principles, there are no general facts that you can bring to bear in your quest for success. All you can do is try something, look at the result, and if it didn't work, try something else. And you can see that basically the hypothetico-deductive method is, in a sense, the basic outline of the general pragmatist philosophy applied to physics.